Start a new topic. So we will have a brief introduction to QNTA because we looked at the distinct time Markov chain. This is a very good application of the idea that we got through the discrete time Markov chain. So we will just talk about the basic of what Qs are, how it is formed, what are we interested in, so on. So as you know that if you have any businesses that happens, okay, in real world, you can view it as a queue. Whenever there is something called as a service that is being offered, and there are some entities who are interested in getting this service. The service is a very general term, so that is what we call as the queuing system. So there is a concept called service, okay, and that is offered by some entities. They are called as servers. So, and this service is something which there is a large number of entities want to get away with the service, and that we will generally use the term customers. Although these terms will be the one that will be followed in queuing theory, but what it may mean different thing in different contexts. For example, you may have a computer, okay, in which many programs will be running. Each one is, will sometimes use the term thread, okay, or a control flow. So they all will share the CPU on using it. So CPU is the server and these are the threads. Or in the internet there may be a service hosted in it, which usually we will call it as the web service. And there are some clients which will get the service. When you have a browser is nothing but a client server, web client, okay. So it will go and then fetch some data for you, and something will run in this web server, and the results will come out and displayed in some manner. So that is one more example. Or in a network, okay, there may be a packet that may come to a particular networking component, okay, it's called a router or a hub or so on. It will process it and then route it in one way or another. So here you will have this as the server and the packets are the customers. Or you may have a telephone exchange in which calls are being made, whether it is in a wired one or even in a wireless one. When you make a call, there is a server which will handle the call. You check whether there is a call can be established. Okay, you should have some radio resources for the call to be established, whether that is there or not. If so, it will allow you. So that is again a customer, server and so on. Service and so on. Or even if you look at an elevator, you take a lift, then the lift is the server and the people who come and then take it is the customers. Or a train and the passengers. So many different kind of things. Or a doctor is a server and then the patients who are waiting the customers and so on. So it's a very generic term, but we will just use only these things. So we have customers and we have a server. Then the normal thing is that the number of customers can be varied. From a society there can be so many people who may like to get the service of a lawyer or a chartered accountant or a server, or a clerk in a government office, or a teller in a bank and so on. So the population of the customer is supposed to be very large. So this is, and there is one server. So here the first thing what we will generally assume is the number of the population is so large that from which the customers come. Okay? But again, all these people are potentially want the service sometime or other. You may not be at the same time. For example, you want to book a ticket for some movie or from train or air and so on. Let us say you have to physically go and then get it, or even online reservation also. That can also be viewed like that. Not everyone will get it at the same time. But the time at which one person gets is independent of the time which others requirement are. Your requirement to go to Mumbai will be independent of others' requirement to go to Delhi. So when you will try to go on, log in and then book, or go to a travel agent and the book, it will be totally different. So they are all are independent. So the nature is infinite number of potential customers are there and their requirements are independent. So these requirements come only when the requirement they will go and then approach this service. Okay. So this is how it is. So then we have to model the request will come one after another. Sometimes there will be a request, another time there will be a request, and so on. We have to look at these things. If you plot it against a time, okay, there may be a request here and here. So it will be totally random. Sometimes it may be clustered, sometimes there may be space and so on. It will be totally random. But you have to characterize it. Then only you can proceed with talking about how this system will work. Okay. So you have to model what is called as the arrival process. Okay. So first of all, what we are going to do is the number of requests that have arrived in a time. Okay, in a time interval. Let us say starting from this to this time, or this to this. If you look at it, it is going to be a random variable. Okay. If you look at one realization, one day between 10 to 11, how many requests has come? Tomorrow 10 to 11, how many requests? They are all going to be random. But we will generally assume that there is some amount of stationarity there. It is not going to change. There can be changes also. In festival season, more customer go to mall. We will not look at all those kind of special these things. So it's going to behave today and tomorrow in a similar manner. From 10 to 11, same as 5 to 6. Again, it may be different. Pressure or may be there. We will not look at all those things at this time. So this is how it is solved. So you can characterize the process first of all. So it is going to be a random variable. Okay. So the time of arrival. Okay, in every hour if you look at 10 to 11, 11 to 12 and so on. So you can now, what you can do is each one is a random variable and you can arrange it in the first hour of a day, second hour, third hour and so on. So let us say the arrival A. Okay, between 10 to 11 and so on, you can get suffixes by which hour you are talking about, whether 9 to 10 or 10 to 11. 9 to 10 means 1, 2 and so on. So you have got random variable and it is also in text, which means you have a stochastic process. It's okay. So the arrival process is a stochastic process. That is why we have used the term process here. Process means stochastic process. So we have to characterize it. Again, what happens? You can also tell the total number of arrivals till a particular time. If you call it as A of t, total arrival till a time t, as t changes, the number of arrivals will change. That you have to characterize. From that you can also find a difference and find how many in an interval can be easily found if you define one of these. So we will know how to characterize this. So first of all, what can you tell about this one? So what I am going to tell is A of t is defined to be the total number of customers who are arrived in the interval 0 to t. You take an arbitrary time point and call it as 0. And from then onwards, the clock ticks at a given time t till number of customers who have arrived, we call it as A. So we will look at some of the properties of it, and we will try to. Some will be obvious. Some of them we have to tell. Okay. First of all, A of t, it represents the count of the number of arrivals that have happened in a certain duration. Or it can be the number of photons that has been counted, or electrons that has been counted by a detector, and so on. So, what values it can take? Negative? No. So it is a non-negative integer value. It's very clear because it is a count. It cannot be negative, and in this case it is an integer. Then I written about t1, t2 or 2 time points such that t2 is greater than or equal to t1. Then what can you tell about a of t2 and a of t1? Huh? A of t2 is greater than or equal to a of t1. Because this is the later time, this is an earlier time. You are counting. Okay. The number of arrivals in 0 to t2. So for example, this can be t2, this can be t1. The number of arrivals in t2 includes the number of arrivals in t1. So this is true. So this is a non-decreasing function. So these two are follows from the way for telling that it represents a count, obvious. So we will give a name for this process which has these characteristics. They are called as counting process. One more thing we will put for convenience, it is not necessarily it has to be mentioned. A at the time t is equal to 0, we will set it as 0. At the start, the count is 0. But it need not be, you can start with some finite number also. Assume you open a mall, there are already 10 people waiting. So it can start at 10, but it doesn't matter. It is only for convenience. A of 0 is equal to 0. Then, no, other question. I have told one that you have an infinite population. So many customers are there. Each person's requirement is independent of others. They don't talk to each other and then come together and so on. No clustered one. Independent entities come separately like that. No, and it is some sort of a stationary that with the time its characteristic doesn't change. Okay? Some characteristic that happen here also happen here and so on. Now, if you look at 4 distinct time points such that this is how it is. T4 is greater than T3 and so on. Now I am looking at the number of arrivals in this interval and number of arrivals in this interval. Before, okay, so what has not been told is if T2 is greater than T2, then A of T2 minus A of T1 is the number of this is the way we have to interpret it. A of T2 minus T1 represents the number of arrivals in the interval T2 to T1 or T1 to T2, whichever way you do. So in this case, what we are asking is, there is certain number of arrivals here, certain number of arrivals here. I would like to know whether they are dependent or independent. In particular, if you are told what is the number of arrivals here, with this, the probability of a certain number of customers arriving in this interval, will it be dependent or independent? Huh? What is your what do you think? See, these are all, there is no prior, you cannot tell it based on your probability knowledge. These are all modeling. You have to, but based on your common sense, you have to come up with this one. But if this is how it is being built, it's like an axiom.
Independent, but similarly, like identically.
No, I never told that their intervals are same. I only told that they are like this one, which I have to again characterize. They are non-overlapping intervals. That is very important. They are overlapping, there can be something. So I will put a question which is more probabilistic, more precise. Probability that A of T4 minus A of T3 equal to N2, given that A of T2 minus A of T1 equal to N. If I ask this condition probability, what can you tell about it? Huh? We can? Correct, very correct. That is, this condition is not going to affect this one. It is equal to the unconditional probability A of this is what the statement they are independent really means this. Okay. So this conditional probability of the number of occurrences, okay, in non-overlapping intervals, they are independent. So we will give a name for this. This is independent increment process. Then we have said more or less what are all the, how it has to be modeled, all these things. But now comes the crucial question. You have to precisely give a prescription for the probability of that in an interval so many numbers will occur. That is probability that in an interval T of T plus tau minus K of T equal to, I have to give it. All these are unknown, but then only we can proceed. Okay. So here it is from T plus tau minus A of T means it is an interval of size tau. This, when we say it is stationary, I really mean that it will not depend upon T. It is going to only depend upon tau. Okay. So this probability is depend only upon the interval size and not on where it occurs. So whether it occurred in this one or whether it has occurred in this one, it's not going to depend upon T. Well, but we have to give a value for this. Okay. So here, what or you have to do, what you have to do is you have to look the other way of actually it has been done is you look at the usual process which you are trying to model, the number of breakfast comings, or you stand in a road corner and then look at the number of vehicles passing and see all these things, and then try to how is the probability looking at? Probability of 3 cars coming in an interval of 1 minute, 5 cars, no car, all these things, and then look it for a lot of time units, construct an histogram, look at the probability, and then come up with a model. People have done this one for different kinds of situations. All have got this kind of a property. Large number of population, independent one, stationary, and all these things. And they have found that so one rule is a dominating one, so that process is one which can act as a good model for us. This is the sentence exactly they will use. So this acts as a good model for these situations. Normal Gaussian process is a good model. So like that. So it is a model, and it is, many times it is good, but sometimes it may deviate out. So this is what we have to find. Well, now again we will do one more thing. What we can do is this tau, based on that it is going to change. But suppose I take an interval which is very small, extremely small interval. So here some customer, some arrival has to occur, or more generally an event. It may be an occurrence of an event, maybe a death, okay, car accident, or a birth, or really an arrival of a customer, or a failure of a component, or something. Okay, that is what we are looking at. All these can also be viewed. So we have to model it. Now the interval size is very small, then only we can really talk about something. Interval size is very small. Now, if you ask, what is the probability that no event would have occurred? One event would have occurred, two event, three event, for everything I have to give a probability. That is what I am now finally confined to. Now what can you tell about it? When the interval size is very small, probability of 2 events or 3 events, 4 events, all these things, I will tell that they are very, very small, negligible when this interval size becomes shrinks so much. So negligible that in the event that the epsilon tends to 0, the probability itself will become 0. Again, why? Because each one of these events are just a number on the real axis, the time at which event occurs. Any two such real number can always be separated out. No two real numbers that is being picked can have the same value. Similarly, two arrivals cannot have the same value. You can always separate it out. So I am looking at such a granularity of time axis that two or more events occurring in that one, that probability will tend to 0. Probability of tend to 0 as epsilon tend to 0. Now, probability of one event occurring, probability of no event occurring. That no event occurring has to have some probability. Because it is not that if you look at all these things, there are places in which no event may not even occur. So those things we have to cross, probability of no event and probability of one event. This is what we have to find. Model. If you look at one event, do you think that that probability can also be said tends to 0 as epsilon tends to 0? Two event is one event. 2 and 1 are just numbers only. So you can also tell that it decreases. But this is a different thing in the sense that when epsilon tends to 0, this can be neglected. It will become 0. It will tend to 0. But here, although it tends to 0, if you in the limit if you make it as 0, then what happens? No event. It means that nothing will occur. Okay, so this we have to give a value. So now what we will tell? Yes, probability of occurrence of one event is finite. It's only probability. Okay, and that is going to depend upon something. What do you think it will be dependent on? About the nature of the process, which we don't know. It may be arrival of customers or arrival of cars or whatever it is. That is something is there. But if you look at it, probability that one event occurs between d to t plus epsilon, that I can change the epsilon. I can decrease it, increase it, and so on. That probability will it depend upon epsilon, the time interval. Yeah, it has to depend. If you have more time interval, the probability will be more. We are not asked about the number of arrivals. Still, we are telling only one arrival will take place because the interval is this one. But the probability will increase. Okay? Obviously, it should be. The more important now I am going to model, assumption I am going to make it. It is linearly dependent upon epsilon. Okay? So this is going to be linearly dependent upon this epsilon. That is where I am really making a claim. Okay? And there is no other proof for it other than that it happens in reality and it's a good model. That's all I can tell. Okay? So it is proportional to epsilon and there has to be a proportionality constant which I will call it as lambda. It has to be something. So lambda can be more or less. If there is a process where a large number of people keep coming, then the lambda value will be good. Where very rarely people come, then the lambda will be less. But the fact that it is proportional to interval size should be true. So this is what I will generally I can make. And there has to be an error in doing this. I can tell like this, it is proportional to this one. But what if someone takes, I will take a finite lambda, I will take with the x, one can take it as 1 second or microsecond, nanosecond or 1 hour also, we will take 1 unit. But it's not, it all depends upon the time scale of the event also. So it is, there can be an error, but I have to quantify, I have to tell something that there is an error. I will mention it as, there is an error, which I will call it as order delta. Okay. Later on we will change it as delta. Delta is a good word. We will change it as delta. By that what I mean is, there is an error. This error is dependent upon delta. When delta tends to 0, the error also tends to 0. So this is again one thing that I will mention. Then what can you tell about this? And again, incidentally, I will also mention about this. This is also a spot error. And that error is just, instead of telling it like that, I will tell there is an error. It's a very small quantity, and that is order delta. Maybe I will mention what this notation order delta is. So now with these things, what can you tell about this? No E. Yeah, it has to be 1 minus lambda delta. Because they have to add up, everything has to add up to 1. If this is lambda delta, this has to be 1 minus lambda delta. Again there is an error, which is order delta. Now, what is this order delta? Okay. Order delta is any function. It's called as an order delta function. It's a function of delta. If in the limit order delta? That is what I am going to define. Order delta is a very generic term, which delta squared will come under this. Delta cube also will come under this. Okay? If you do a sort of a Taylor expansion or something, then the second order will be like that one. But in general, it can be any term which has this property. It's called as an order delta function. Okay? For example, 2 delta will not figure out like it's not an order delta. But 2 delta squared plus 3 delta cube are all order delta terms. Okay? So this is how it is. So what I am telling is, all these are true, I am giving some error, but I can make the error as small as possible by making delta smaller. Because the error, this will be error is order delta, here is order delta and so on. So only if it has this property it will. So this is what it does. Now, with starting this has these are the basic axioms. You can now find out what will be the probability that A of t is equal to n. By setting up a differential equation and so on, I am not going to do it. Usually this being done in the next level of class, stochastic modeling and this. You can easily tell. You can divide into p plus epsilon, okay, p plus delta and so on. Probability that the A of p plus delta is equal to n can be of only 2 ways it can occur. N minus 1 here, 1 here, or n here, 0 here. And then write out an equation for that. And then you can bring terms together and then write a differential equation. Okay, d by dt of, we will use a term P of A of t is equal to n. Okay, you can write an equation of P n of t. So you will have a differential equation for P n of t is equal to and so on. And then finally get a form which will have this kind of form. Okay. So if you do all those things, finally you will get a formula. What it does is the probability that A of t, the number of events that has occurred in a time interval of duration t, for it to be equal to n, is given by e power of minus lambda t power n by d, where lambda is a parameter. For n, for t greater than or equal to 0, okay, n has to be a non-negative integer, and then lambda is a parameter. And this process, this stochastic process is called as what? Poisson stochastic process. If you fix t, then it becomes a Poisson random variable. In Poisson random variable, only difference is the Poisson random variable x equal to n is given by formula where e power of minus lambda power n by n factorial. But here what happens here is this random variable, now you are telling that it is the number of variables in a duration t. It is a function of t. For a different t you will get a different random variable, and that is why the parameter becomes lambda t instead of just one quantity lambda. Okay. So, because there if you fix the value of t, then you can call the lambda t as some other lambda or some other beta or whatever it is. Then it becomes the familiar Poisson random variable. Now it is dependent upon t. So, if you look at, you know that if you fix a t, this is the probability, and now you can find what is the expectation of A of t. What will be the expectation of A of t? It's a Poisson, once you fix t, it's a random variable, Poisson random variable. What is the expectation of Poisson random variable? Whose PMF I have given? Lambda t. So, what it tells is the expected number of variables in an interval of size t is lambda t. So, I can interpret this parameter lambda as the rate at which events occur. So, rate times interval gives the mean value, expected value. So, lambda is the rate. So, because it is Poisson, it is called the Poisson rate. So, this is how we will characterize the arrival process. The arrivals can be modeled to be a Poisson stochastic process, which has got all these properties. Next, one more thing that we need to also understand before we move on. One thing is, now A of t, now how do we actually write it? A of t greater than or equal to 0. Okay. Is a stochastic process, Poisson stochastic process. What is the nature of the stochastic process? By that I mean, in terms of the 4 classifications that we did, what can we tell about its state space? Whether it is discrete or continuous. Discrete. What do you mean by state space? The value, the random variable state. Here the random variable's value that it takes, it's the count. It is a number, non-negative number. So it has to be discrete. The parameter is continuous because you can ask at any given time. So it is a discrete state continuous time stochastic process. Okay, that is at any given time, if you mark the events at any given time t, you can ask what will be A of t. For function of t, but that itself is random, but you can, that's what we are trying to calculate. There is one more way of also giving, you are actually telling which event has occurred at what time. First event has occurred here, second event here, third and so on. Then given any time t, you can count the number of events and that is what here. This is one way of specifying. Another way of in which I can specify the whole thing is how long it took for the first event to occur. After that, how long it took for the second event to occur from the time the first event occurred. That is called the inter-event time or the inter-arrival time in case of question. That is and so on. So that I will use another notation tau, and is the time for it is the inter-arrival time between n minus 1 and the nth customer. Okay, so for the first customer T1, it is between the 0th customer and the first customer. By that I mean starting from time 0, what happens? From the third customer, it is between the second and third, we will call it as third. Okay, this is how it is. So you have got tau 1, tau 2, tau 3 are all the inter-arrival time between 0 and 1, 1 and 2, 2 and 3 and so on. What can you tell about these quantities? Are they random variables? Tau 1, tau 2, tau 3 and all.
Yeah.
They are random variables because you can't predict. Between the third customer, then the fourth will come, you can't predict. It is going to be a random variable. So you have a sequence of random variables. It is in touch. So this is also a stochastic process. Okay. So if I know this, I can construct this. I can construct AF. There are two ways of specifying this thing. Because start at the time 0, after tau 1 I put a point, after tau 2 I put a point and so on. I know all these points. If you ask at any given time, I will count and give you A of t. So two ways of specifying a process. Now, what can you tell about this process, tau process? In terms of these, again characterization, that is in terms of the nature of the state space time and all, tau. What is the nature of the state space of the tau process, inter-arrival time process? Tau 1 and tau 2, what values tau I can take? Continuous. Continuous state. Then discrete parameter, because you are telling which one, that is this 2, 3 tells about between which two customers and so on. It is a discrete parameter. So these two processes characterize the same thing, but look at these things. It's quite, this is a discrete state, this is a continuous state. This is a continuous parameter, this is a discrete parameter. Okay, stochastic process. Now my only thing is, now what I want to just characterize it, probability. This tau 1, tau 2, do you think there will be IID random variables? Yes. Why? First of all, the process is stationary, so nothing changes, it doesn't evolve. So that is one thing. then this is similar to the independent increment nature. You are waiting, one event has occurred, from the time one event, another event has occurred, and so on. So, they have to be IID. So, I have to only characterize any one of those random variables. So, first I will try to find out the CDF of tau I, the general I, to be less than or equal to this. Equal to 1 is what I am going to ask. But what I know that the overall the process is Poisson. That's what I know. To do that one first, it is easy to talk about the CCD. What it does is that take any inter-array. Probability that the inter-array is greater than this is the question I am asking. Where arrivals occur is a arrival process, a counting process, and it is Poisson in nature, which is given by this. What can you tell about this? How do you, how are you arriving at it? What you know is that the number of arrivals in any interval is equal to n is given by this. That is already we have arrived. Now I am asking is, the inter-arrival time has to be greater than this. If the inter-arrival time has to be greater than this, how many arrivals should have occurred in this? From one arrival to another arrival, it has to be greater than this. That's all I have asked. Huh? It has to be the number of arrivals that should have occurred in that interval has to be 0. Both are one and the same. Both statements are correct. When I tell that, when the inter-arrival time is greater than s, means one customer has in this at this time, the next customer has not arrived. Which means that after that, here again, so many can be clumped. Many things can happen. I don't care, but no one should have arrived in this interval. It means that the number of arrivals here is equal to 0. Which means that from the Poisson principle, it is e power of minus lambda into this duration. Why? See, if the duration is yes, then it is a Poisson random variable with a value lambda s. E power of minus lambda s power 0 by 0 factorial, which is equal to e power of minus lambda s. So, the inter-arrival time to be greater than s is equal to that probability that no customer has arrived in an interval of duration. So, that CDF has this value. So, the CDF has this value. So, what can you tell about tau i's? There are exponential random variables. Okay? So tau i's are exponential random variables. So it is a very generic statement that if we have a Poisson stochastic process that tells the number of customers arrivals in certain duration, then the inter-arrival times has to be exponentially distributed. Or the other way also, if we have certain events occurring so that the time duration between two events are exponentially distributed, then the number of events occurring in an interval has to be Poisson. I will give an example what it means. Suppose what you do is you have a bulb, you take it from a bag, from a carton, and then keep replacing it. As soon as one fuse, you keep the another one. The lifetime is being characterized as an exponential random variable. So, the moment you place it, it will live for some exponential distributed amount of time. Then again you keep it. So, the time duration between the replacement of the bulbs are exponentially distributed. So the event is replacement of a new bulb. So now if I ask the question, what is the probability that in 1 year I should have replaced 6 bulbs or 5 bulbs and so on? It is same as a Poisson stochastic process, okay, varying with the same lambda. What I have to do is the rate, the lambda is this one, okay. So because this is exponential, event are exponential, the process has to be Poisson. So this is how we can model the arrivals. Now we have to model the server. We can generally take the service time is exponential. Exponential in the sense that it is also exponential random. We will tell the probability that the service time, we will call it as SM, the service time of the nth customer, to be less than or equal to some S equal to E. We will use another rate mu S for this. This is how we can model the service. This is done for convenience. It not necessarily will be the case. So we have modeled the arrival, we have modeled the service. This is there can be other models also, depending on what situation we take. So which we are going to now look into how the queues can be looked. We will characterize the queues and then we will come up with what are part of the on queues, and this much we will study in the next lecture.